Hello and welcome to our Design Day video. We are team 21057 and our project is the STROBE, the SWIR Transmitting Optical Beacon. This project is sponsored by Elbit Systems of America and our team members are Caitlin Archibald, Jeremy Dower, Kayla Philippek, Garrett Hartung, Louis Kaplan, and Adnan Taleb. Here is our team photo. It was taken over Zoom this year due to COVID restrictions. On the top row we have all of our optical engineers, and then on the bottom row from left to right, we have engineering management, electrical engineering, and mechanical engineering. Jeremy Dower was the team lead on this project, and Adnan Taleb was the procurement lead.
Moving forward with our introduction and problem description, a little background on our project is that short-wave infrared beacons have been used by the military for marking targets to be destroyed, landing zones, and allied troops to prevent friendly fire. And our team designed a device that can mark a target in the field by emitting at 1550 nanometers, be detectable to those equipped with SWIR vision technology, be small, portable, and rugged, be bright enough to be seen from a distance, and the device is going to be controlled remotely via Bluetooth connectivity through our team's custom designed app that allows for powering the beacon and changing the pulse repetition rate. Up to 3 individual strobe devices can be controlled using the same app with our project.
Here is our system block diagram. First on the left you can see we have a remote control, which in this case is an Android phone that will be utilizing an app to control all 3 strobes independently. This will then send a signal to our Bluetooth receiver directly connected to the Arduino Nano. Both the Bluetooth module and the Arduino will be connected to a custom PCB that our electrical engineer has made. This will direct power that is received by the power supply, which consists of AA batteries, to the 6 emitters and our Arduino. The large blue box signifies what will be inside the strobe package and what will be outside of it.
Our materials and methods section was broken down into 3 subgroups of engineering. Starting with the optical engineering subgroup, the irradiance and field of view was tested and replicated in light tools to make sure they matched the specs given to us by Elbit. Then we went to lab testing using an infrared camera and pyroelectric radiometer to ensure that the emitters were emitting at the specifications given to us by the company. The mechanical engineering subgroup involved designing and fabricating the system packaging in SolidWorks and printing it using 3D printing. The electrical and computer engineering subgroup involved designing and incorporating a microcontroller and HC05 module to interface with a smartphone application. This lets us use the Bluetooth capabilities. Voltage regulators were used to moderate current supplied to the emitters, and a MOSFET was used as a switch based on the output of the microcontroller.
Here we have our system verification table with the system requirements on the far left and the results of our verification testing on the far right. The center region of the table details the references that signify a pass for each respective module, along with the measured value for our system. This slide in its entirety encompasses all the performance requirements for our project, starting with the runtime. Our requirement demands at least 30 minutes of continuous runtime, and our measured value indicated around 39.5 minutes of runtime, which results in a pass for this requirement. The next 2 requirements are tied to operation, function, and control. An app interface is in the works and displaying promising results. However, since these 2 requirements are yet to be verified, the result is to be determined. As for the next requirement, they all passed, starting with radiant power, which was required to be greater than 150 milliwatts, and our measured values fluctuate between 185 milliwatts and 125 milliwatts, normally distributed, which is sufficient to result with a pass. Output power needed to be less than 20%, and our measured values show 19% above the ideal irradiance of 150 milliwatt per steradian and 20% below that, which is also a pass. The output angle was required to be between 120 FFOV and 140 FFOV, and our measured value indicated an FFOV of 120, which is within range and thus also a pass. As for the output wavelength, the requirement was 1500 nanometer, and our selected emitters emit at exactly 1550 nanometer, which is within range and is also a pass. Lastly, the strobe needed to function with a 50% duty cycle, and it was determined that the strobe can output with a 50% duty cycle without an issue, which of course results in a pass. Here is the rest of our verification table, the section concerning design feature requirements. The first requirement is regarding specific dimensions for the size of the strobe. Through measurements of our latest strobe housing, the result is a pass. This next requirement is regarding shock absorption and rubber shelling. Since it is not a main priority for our proof of concept, it has become a strong suggestion for a mass-produced model in the future. As for our strobe, it is not applicable. Next is a deployment requirement, which specifies the deployment parameters. The strobe does not remain stationary at a slant of 45 degrees when dropped, but will remain when placed. Although it is close to success, this requirement result is a fail. Next is the weight requirement, which states the strobe shall weigh less than 6 pounds. Our measured weight currently sits at 4.98 pounds, and thus results in a pass for this requirement. As for the reusability requirement, we needed the strobe to be reusable after battery replacement, and with our proposed design and the easy-to-access battery compartment, this requirement results in a pass. Lastly, for the last two requirements regarding durability and temperature of the strobe, both requirements have yet to be tested and verified, as we are still in the assembly stage.
This slide shows our design concept. The first figure outlines the design of the PCB. This includes resistors, MOSFETs, a microcontroller, a fan, a Bluetooth module, and varying trace widths depending on the expected current at those points. The second figure is our completed mechanical system. This diagram is an exploded view, and it shows how our strobe looks as well as the storage of crucial components such as our power supply at the bottom, electronics in the upper middle, and our emitters at the top. The third figure is our light tools analysis. This is a radiant intensity plot. It shows the intensity in watts per steradian over 120 degree FOV. If you look at the center of the diagram, you may notice the large spike in intensity. This spike falls within our 20% tolerance when we compare it to the outer field of the analysis.
Here are some examples of the drop tests we conduct in our devices to see if they land upright when dropped from certain heights. Our first experiment had a 55% success rate of landing upright on its base, but after making some more improvements and printing a new model, we were able to bump that up to a 75% success rate on our latest model. Each of these experiments had at least 40 trials to ensure accurate data.
Here's our PCB. We have it configured for one LED right now. We will be using the Bluetooth terminal application to send on and off signals to the gate of the MOSFET. B is our flicker state, so when we press B and send it, it'll flicker the LED on and off. A is our continuous wave, and C is our off. Once again, we'll show you the flicker, and that's the demonstration.
Here we're doing darkroom testing of our emitters using a pyroelectric radiometer. We determined that the radiometer emits about 88 microwatts onto the detector. We predicted an emission of 95 microwatts. This is really close to our predicted value.
Finally, we would like to thank Mike Knopfziger and Miriam Baker as our mentors, Matthias, Whitney, and Jeremy Jackson as our sponsors from Outlet Systems of America, John Koschel for his help with radiometry guidance, Lee Abel and Devin Mullen, also engineers at Elbit, and Craig Pansing from the Synopsys Help Desk, who helped us out with light tools.